Thank you, Nigel. Right. So as Nigel said, we're looking at building bridges with GSA. Now, we look at a number of particular areas within this. So the modelling, influence lines, the loading optimization, enveloping, footfall, and a few examples of where GSA has been used for bridge design. So the bridge modelling, first of all. Some people sometimes ask me, what is the difference really between a bridge and a building? And in essence, really, buildings are complex structures with simple loadings, but bridges are simple structures with complex loadings. And so the loadings is a crucial aspect to the bridge design, which I'm sure you know. And in terms of the modelling aspect, an important thing to know about is the alignment. An alignment, of course, is a road term, and we can define these alignments in GSA in terms of the chainage from the start point, and that start point is the 0, of the grid plane, and then there's the curvatures and the radiuses, because being a road, you need to have curves and transitions between them too, and you can define all these in GSA. So let's have a look at that. Let me hop over to GSA. Now the first thing you need to worry about is making sure you can actually do the bridge analysis. So you need to make sure the bridge part are activated in your preferences. Let's just start a new model. Let's maximize that. So first of all, we need to find a grid plane for our alignment, so we need to find the axis for that first of all. And I'm going to create an axis just by creating 1 in 4 slope to begin with, and then an additional point just to set that up. And I'm going to select those 3 points, and I'm going to use this create user axis, and that's what I want. X is a 1 in 4 slope, Y. Well, 1 in 4 slope on plan, and Y in that direction, and let's call that axis deck. And then I can delete those 2 points there. I'll leave that one on 0, 0, and I'm then going to create a grid plane, which I'm going to call deck. Axis is going to be deck. Elevation, all elements, 2-way spanning, and let's make that. Just make sure that's the current grid, and I'm also going to create a new layout just at 3 meters, because we need to for this bridge I'm going to be creating a 3 by 3 meter grillage for the analysis. So let me draw in, hold the control down so I can do multiple points. Alright. And now let me just select those and make sure they are property 2. So I'm going to use property 2 as the deck part. I'm going to have property 1 going around along the bridge. Now to find the bridge, I also mentioned we need to create an alignment. So let's get on the bridge section, and this is going to be, call it bridge alignment, something original. And the details of this, I'm going to start off at 0 with a right hand curve, radius 50 meters on the deck plane, and then at 25 meters is also a right curve, 50 meter radius. So this will create a circular curve over the first 25 meters. Then at 50 meters I'm going to transition into a left hand curve which has a radius of 100 meters. And then at far end of the deck, I'm making the bridge 90 meters long. Again, a left curve 100. So what we have, if I just stick that up at the top and scale this on my diagrams, I can now show that alignment. So there we have the circular curve, transition, and the circular curve in the other direction. Now, having defined this alignment, I can use these elements here, select elements, to create the bridge deck as a whole, this bridge grillage. So under the sculpt, I've got a extrude selection. Now, extrude is one of those wonderfully useful commands, and especially when we're doing bridges, because it can pick up alignments. If I say, well, 90 meters long, so 30 increments at 3 meters, and include beams along, and lo and behold, we have, let me switch that grid off, the bridge defined. And because the elements drawn in were defaulted section property 1, and the elements going across, I changed property number 2, we now have longitudinal and cross members already set up. Make it nice and easy for us. So let's define the sections, and before I do that, define the material. So there's a concrete bridge. I'm going to create a use defined concrete material, which, as I said, is the concrete. And because I'm using Eurocodes, I will create a Eurocode concrete. We do have a number of other codes, but concrete, Eurocode concrete. And I'm going to make that the default property. So longitudinal T-beams. Overall depth a meter. Now we're 3 meter spacings. Flange 500 thick, and the web. This is the deck. Nope, got the wrong way around. That's better. Flange, deck, web 500s. And I'll also create a slab element, which can be a rectangular 300 and 3000 wide. Now, if you want to minimize the torsions in the deck part, what we can do is we can go in and modify the individual analysis properties, and let's just halve the torsional stiffness. But obviously this is a engineering judgment on the properties. Let us look at this and make sure it's all gone in correctly. That looks promising. There's my T-beams. There's my deck elements. That looks great. Wonderful. Now, we now need to create some support points. Now, I'm going to pin at the end. I use the keyboard to rotate the view a bit, make it easier to select. And then on third points, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So third points, modify those and pin them. Right. Now to check this model's all good, I'm just going to create gravity load grillage. Half the weight. It's not quite accurate in this particular case, but it will suffice for the moment, because obviously the two elements are not equal weight. So let's have a look at the results here. So bending moments all look sensible. Deflections, I see we've got extra deflections in. Maybe we could optimize this by moving the supports out a bit, but in this particular case I shall leave it as it is. Okay, let me just delete that and move on. So that's a bridge setup model wise. Let's look at the bridge loading optimizations. Now, one of the most important things about bridge loading is a thing called influence lines, which, as I say, give us the effect of a moving load at the point. In this particular case, this diagram here is moment at the support point, and you can see this loading here has quite a large effect, loading here has quite an even larger effect, loading over here a small negative effect. Now they only give the results for the selected points, so you need to select these points and select sensible locations, which means don't look at every point, because you'll find with bridge loading there will be hundreds of load cases, and And so you've got to try and cut these down to just the essentials. Now, once you have all these loads defined, you need to then envelope them, and you have to be so you have to be careful because the number of permutations can increase very rapidly. For example, if you've got two combinations, one has 5 permutations, one has 6, envelope two together, you suddenly got 30 permutations, and the highest I've heard of is 500 million, which will take a little while to analyse. You can put operators onto the envelopes, but you will lose these coincident effects. But you can also do an analysis envelope, which is a slightly different thing, and I'll look at the two examples in a minute. So the permutations, there's your options. Top diagram, the envelope. That's straightforward. Second op, say just take the max of that envelope, and the third one is take the sign absolute value of that envelope. So you can see you can get different numbers out to worst values, but use with judgment. Now when it comes to putting the loading on, the GSA help does have a step-by-step guide to cover the various methods, and there are 3 methods in total. There's full optimizations for the Euroco's UK and Hong Kong highway loadings. There's also lane-by-lane optimizations for a large number of other country codes, and there's also, you can also place vehicles directly onto the model. Now I'll be looking at the first two. We won't have time to look at just straight vehicle loads themselves, but that's straightforward. You can also look at the analysis stages in the for actually constructing the bridge. Now there is a separate presentation online which you can look at, which goes in quite a lot of detail, and again we're just concentrating on these first 2 options today. So bridge load optimization, let's go back to the GSA model and put some bridge loads onto this. Now first of all I need to make sure my bridge loading is specified, and these options down here, these are ones for the automated loadings, but I'm going to go for an undefined and then Eurocode loading. So I'm going to create loadings on this bridge manually, if I want to the word. So then go down to my bridge section, and I need to create some paths which go onto this bridge. So let's just tile these windows, and so I'm going to create a lane 1, which is a lane type, and it's going to start off 1 meter from the edge and 4 meters. And you can see the alignments have started to appear on it. Let me just add in the labels. You see the lane centre line and the lane edges. And create a second lane. And this goes from 4 to 7. And then finally I'm going to create a train track, which is a track type. And you see this is slightly different. This gives the centre line this time over at 8 meters, and I'll take the default properties. So we've got 2 lanes of traffic and a railway line on this bridge. We now also need to create the node, the influence points which we're interested in. So I'll do the nodes first of all. So this bridge, okay, for the vertical reactions we'd actually need 4 sets, but I'm just going to take this line here just for simplicity. The others are the same, and so these are going to be the nodes 41 to 44. And so I set my defaults to false. 41, take the defaults. 42, 43, 44. And let's just check on that. We add in a new diagram, which is our influence effects, and you can see there's the support point. So we're going to be optimizing our loads to maximize the reactions at this point. Similarly, I want to maximize the loading for the moment at this point, target moment. So let me switch on my beam elements, 74 to 77. So it's beam. I'm going to change the grouping to 2. Beam 74, 75, 76, and 77. Change the influence effects to the beam just to make sure they're there. Yep, you got that right. And I'll also take the mid-span moment on here as well, which will be this line. So I'll take 39 to 42. So I should change my grouping. 39, 40, 41. Let's just check that. Wonderful. So we have our influence points set up. We have our alignments and paths set up. We also need some loadings. So I'll go to my path loadings and say in lane 1 I'm going to use a Eurocode lane 1. Second lane I'll choose lane 2, and for the track I'll choose this train load. So let's trim these down. Right, now got our influence points. Let's do an influence line analysis on this. So bridge optimization analysis, influence analysis, and analyze. Think about it for a moment. What we now have is some alignments, influence lines. So let's look at the new diagram. Under the global results, the influence line. So the influence lines. Let me just switch off the. So here is the influence line lobes for that support point. And if we look at the influence line for the hogging at the beam, you see we get 2 lobes at that point, and similarly the for this mid-span moment. Now we can also look at these lobes in more detail. So let's go to my Lobe Details. Let's think about it. Let me go different results. Okay, that's better. Right. So this lobe, these influence lobes here, you can see for the line we have 3 lobes, 1, 2, 3, and start the interchanges of these lobes and the largest value, and you can see path number 1 is actually has the largest effect. Well, it's a slightly longer span as you expect, and so on. So now we've got these, we should be able to do a optimize loading on these. So it takes the influence line analysis, and let's look at what we have. So we now have a large number of static bridge loads. Now these loads are grouped. You see these first lots are for the hogging moment, and group 3 beam for the sagging moment, and the node influence effect for the result, the reaction. Now, some of these will be unimportant. For example, we might say, well, I'm only interested in I could remove uplift off this off the support, or alternatively I could say for the support point I want the maximum moment, but I can get rid of the minimum moment. Some of those are getting reasonably large, but you can see on the group effects column where some of the 10 to 6, some of these 10 to the 5. The 10 to the 5 ones are going to be small, so you might be able to ignore them. I will leave all these in. So what I'll do now is expand the bridge loading, and what this will do is let me just get rid of the influence lines. We now have a whole series of loads on the structure. I'll put that back in. Creating this first 3 maximum moment there, minimum moment at that point, the mid-span moment, worst cases, and the worst case support reactions. Now we have all these analysis cases. What we can now do is a static analysis on all of those default cases. And of course what this gives us are bending moments, deflections, reactions, and so on. Now there are quite a few of these, so what we need to do now is enveloping. Now the envelope, we could take an envelope of all of these. Now with a large model, I'm just copy that for later, as we'll see in a minute. We could take envelopes. Now a large bridge model, that enveloping display can take a little while, but let me show this a little bit better. Reduce the display and just create a list of one of the beams. As I was using the keyboard shortcuts for rotating the view, very useful. Save that as a beam 1, and that's just display. And you see there is the envelope of the bending moments on that beam, or alternatively the shear forces. Now, as I mentioned, that can take a long while for a large model. So what we have in GSA is an analysis task, which is an analysis envelope. And what we can do here, notice I saved that little list from earlier, and I can say in this analysis I want the worst reaction forces and the worst major axis moments, and analyse that. It's done. So rather than a single envelope, we actually get maximum and minimum moments. So it's works out slightly differently, but you still get all the results there. Now that is a lane by lane analysis, which you can do for just about any code that we have supplied. But what if I just what we can do with the Eurocode, if I just strip this back, now I will leave the, did I say delete your path? I'll leave those influence lines, and I'll delete out the path, because I'm going to create a full Eurocode analysis. You can see, so the Eurocode things are a lot quicker when you're using the Eurocode or the UK or the Hong Kong codes. So this time I am going to create a carriageway. Now, whilst in the UK codes, the one-way and two-way carriageways make a difference because the direction of vehicles is important. It doesn't make a difference in Eurocodes. And this time it's going to go from 1 to 7. So there is my carriageway, and I'm also going to create a footpath or footway, as you prefer, and it's just a little bit offset, and you see there's a small reservation between the vehicles and the pedestrians. Now when we do a bridge analysis on this, rather than all the individual stages, what we can now do is everything at once, from inference analysis right up to static analysis. Takes a couple of moments. Wonderful, it's finished. Let's look at our results. So we have all the various bending moments as before, which we can then envelope just like we did with the previous load case. And of course, being Eurocodes, you need to apply partial factors and combine them with a dead load, etc, etc, etc. So that's bridge loading. Now another aspect of bridging is, of course, is pedestrian loadings, in particular footfall analysis. Now footfall, we mentioned footfall on bridges. A lot of people think of the Millennium Bridge. Now you have to remember that the Millennium Bridge was horizontal excitation. What GSA looks at the moment is the vertical excitation of the bridge from people walking. Now, so it's all to do with the vibration of the bridge. And the example, the bridge is a simple supported beam, single span, and you have a mode of vibration. And when somebody jumps or puts a foot down on the middle of the bridge, you get a vibration which gradually dies off over time due to the damping of the bridge itself. Now there are actually several modes of vibration. There's the first three, in our simple case, and if we use our bridge as an example that we just built, the modes are a little bit more complicated than the examples on the left, but the principles are the same. So we need to find all the relevant modes. Now once we have the modes, there's a thing called the modal mass then becomes important. The modal mass is essentially how much of the structure is actually being moved in that vibration. And so this simple case, this would actually be half the mass effectively is being moved. Yeah, nothing in the middle, everything in the middle, nothing at the ends, everything in the middle, and yeah, it works out as half. Now this is important because force equals mass times acceleration, or to rearrange, acceleration equals force over mass. So the force is the foot forces, people, the heel drop forces. The mass is the mass of the bridge moving at that point, and so more modal mass, the less acceleration. And accelerations is what we're after, and velocities too, but accelerations mostly, which are all derived from the vibration. And from these accelerations, we then get a thing called a response factor, which is a measure of human perception to vibration. And you note that people are most sensitive, range of about 4 to 8 hertz vibration, less sensitive for low vibrations, much less for higher vibration frequencies. Note people are more sensitive to horizontal vibrations, but that's another question. So how do we go about doing that? I go back to GSA. Now rather than doing the footfall on this grillage model, it's much better if we can use a 2D element model such as the one I have here. Now This is because when it comes to footfall analysis, the detail of the deck is quite useful. Now, we used to have to say that you had to use quad 8s for this sort of analysis. You can now get away with quad 4s due to the new 8.5 2D element properties. So what we do is an analysis task, which is a modal analysis. I need to find the modes up to 15 Hertz. So if I just take 30 modes and say I want all the modes up to 15 Hertz. I'm not interested in modes above that. I can also apply additional loads. If I had some super dead loads in here, I can include those. And this is the self-weight coming in. And let's analyse that. So we asked for 30 modes, and GSA's actually kept just 19, the 19 that we need. Let's look at the results we get. So displacement contours and displacement shapes. You see there is the first mode, second mode. I'll just quickly run through these, make sure they all look sensible, nothing untoward. Wonderful. They look good. Okay, once we're happy with those vibration modes, we then need to do a second analysis, which is the footfall